It's Thursday, April 2nd, and this is Nighttime Mathematics Radio. Format of the show is always the same. You tweet your questions to me on Twitter, at NightMathRadio, and I'll try to help you out right here live on the air. So, in this world where the classes have stopped apparently forever, but the homework goes on and on and on, we can help. Let's take a minute or two for people to ask questions in on Twitter, then we'll try to help people right here. Welcome back, everybody. This is Nighttime Mathematics Radio. Once again, if you have any math questions, you can tweet them in on Twitter. But for the moment, we have an interesting question. Some folks earlier were having some interesting problems with a pre-calc question. It's a pre-calc question involving, as it turns out, particle motion. So let's take a look at this. So the question looks like the following. Students are asked, said, if the acceleration of a particle is given by a of t is equal to minus 3, and if the velocity at t equals 0 is equal to 15, then sketch a graph of the particle's velocity. So first sketch a graph of the particle's velocity, and then the other question they ask, which is a very typical question in this sort of problem, is find the value of t when the particle is at maximum height. Now this is a problem where the assumption here is that you know pre-calc. If you know calculus, it's actually a little easier, and we'll talk about that midway through the problem. But let's start by assuming you know pre-calc. In a pre-calc class, typically what you're told is, if a particle has constant acceleration, which is what this is, because notice the acceleration function is just a constant function. It doesn't matter what t you plug in, you just get minus 3 back. This is about the simplest function you could possibly have. This is a function where the value isn't actually a function of the input variable at all. The input value is t, and no matter what t you plug in, I give you 3 back. This is what's called constant acceleration. This is as simple as it can get. And given that, a pre-calculus book will give you formulas for the velocity and the position. It will say the velocity is given by the velocity at time 0 plus the acceleration. This is, again, given constant acceleration. And the position at time 0, which you can call x or y or whatever you want. I'll call it x because I'm bored. Is equal to the initial x position, which, you notice, we're not even told in this problem, but we don't need it for what we're told. Plus, oops, v naught t, v naught plus a t. There we go. Obviously losing my mind slightly. It's that kind of week. There we go. The velocity is the initial velocity plus a times the time. And then the position is the initial position plus the velocity at time 0 times time plus 1/2 times the acceleration times time squared. You'll notice these are the three simplest functions we know about. This is a constant function. This is just a line, or a linear function if we're feeling very formal. Why is it a linear function? Well, it's got a t-intercept, or I guess a v-intercept here, and it's got a constant times time. And notice in this case we know both those constants. In this problem we're given a is equal to -3 and v naught is equal to 15. So in this case we know v of t is equal to v naught, 15, plus a. Well, a is -3, so it's -3 times t. And you know exactly what this is. This is a line. It's got slope -3. It's got what you'd normally call y-intercept 15, except in this case you notice the two variables aren't x and y like they were when you're looking at lines. In this case, the axes are the t-axis, the time axis, and the velocity axis. So in this case, we don't have a y-intercept, we have a v-intercept, and our v-intercept is 15. And then it has slope -3, so it goes sharply downwards. And you can see that this becomes 0. We can find our t-intercept by solving for 0, just like we'd normally find an x-intercept in a simpler problem. So 15 is equal to 3t, or t equals 5. So when t equals 5, it becomes 0, and then it becomes negative, and it goes on forever. And this is just plotting the graph of a line. This is like everything else you've ever done. And the cool thing is you know exactly when it reaches maximum height, because you notice, this is where I was thinking about this means. Over on this side of 5, the velocity is positive, which means it's going up. So we assume that this is, in fact, the up direction motion. They don't actually say that, but that's okay. It's a sloppily written problem. That's fine. Then it goes up slower and slower and slower, stops when t is equal to 5, and then begins going down again. So at what time does the particle hit maximum height? Well, time 5. T equals 5. And if we wanted to, we could go on and plug values into this and see that it's in fact moving in the third thing, which is this is a quadratic function. And see that this thing is in fact moving in a parabola. But that's not necessary for this problem. This problem just asks about the velocity. Now, I mentioned this problem looks substantially different if you do calculus than it does if you do pre-calculus. And the reason is, in pre-calculus, these are 3 separate equations. Right? We have... I'll skip to another page for this. In pre-calculus, we have a is equal to -3. We have v is equal to 15 minus 3t. And then we have x is equal to, and we can plug in the values now again. We have x naught, which we don't know, plus 15t minus 3/2 t squared. And where do we get each of these? Well, we have to remember them or look them up in the book. In calculus, it's much cooler. In calculus, we're told, What is the acceleration? Well, it's the second derivative of the position. So if we're in calculus, we could now say, well, I want to know the velocity. Well, the velocity is the first derivative. I've got a second derivative. I should integrate. And I'll integrate from time equals 0 to time some t later. And often people put a dt prime or d capital T or something stupid to try to indicate this is a different variable, but I don't care that much. So what does this give me? This gives the integral of the second derivative is the first derivative, evaluated from time 0 to time t. It's equal to, this is just minus 3t. Well, this tells us that the x dt at time z, or in other words, the velocity, minus the velocity at time 0 is equal to minus 3t. But we know the velocity at time 0 that was given us in the problem. That's 15. So v of t is equal to 15 minus 3t, just like we were told. So you notice this is exactly what we got before, except before we had to plug into a magic formula that appeared in the book, which we believed because it was in a blue box. And this time we know it because we just got there by integrating. And we can do the same thing again. We could say, okay, if dx dt is equal to 15 minus 3t, and I want to know what x is, I could say, okay, well, once again, integrate both sides against time. 0 to t is equal to the integral 15 minus 3t dt, 0 to t. This gives me x at time t minus x at time 0 is equal to 15t minus 3 halves t squared, minus zeros, because when you plug 0 into this, it just vanishes after integrating. So x of t is equal to x at time 0, and often we just write that for short as x sub 0, plus 15t minus 3 halves t squared. So the cool thing about doing calculus, as opposed to having to do this with pre-calculus, is that you don't have to memorize any of the formulas. In pre-calculus, you have a large number of formulas that appear in blue boxes, and you're forced to believe them because, as I say, they're in blue boxes. And if any of you out there have taken statistics before you took calculus, you might have noticed that same property. You get formula after formula after formula that appears in blue boxes, and you're forced to believe them because, hey, it's a blue box. It must be right. That's because statistics fundamentally is based on calculus. If you have calculus first when you take a statistics class, you actually derive formulas, and it feels very much more like a math class. But if you take statistics first, we can't derive any of the formulas, so all we can do is show you blue boxes and hope that you're okay with that. This is basically why calculus sits where it does in the math sequence. And linear algebra is in a very similar position, as it turns out. And again, it's the basis of a whole lot of other work. Okay, this is Nighttime Mathematics Radio. If you have any more questions, feel free to tweet them into Twitter or at Night Math Radio. I'll try to answer them here live on the air. This is Nighttime Mathematics Radio. Welcome back, everybody. This is Nighttime Mathematics Radio. Once again, this is a show where you can tweet your math questions live on @NightMathRadio on Twitter. I'll try to answer them right here live on the air. This show airs weeknights at 9 p.m. Pacific. It goes on until we run out of questions, basically. Or until I just get too tired and the math gets too wrong. Now, someone earlier asked a question about linear algebra of all things. They said, well, I don't understand what eigenvectors are. People keep talking about eigenvectors and eigenvalues, and I just don't know what they even are. That's a good question. Let's take a look. Now, if you're in a linear algebra class, you've seen matrix after matrix after matrix after matrix. You get matrices that look like this. And I'm making this up completely off the top of my head. I didn't make up one that has nice eigenvalues and eigenvectors. I just said, well, what is this thing? And the answer is, well, what we're looking at here is this. This is an operation that acts on two vectors and gives us back more two vectors, where the first entry in the two vector, if I feed it some two vector AB, what it gives me back is A plus B for the first row, and minus A plus 3B for the second row. And that's great, but it's a little hard to see what this matrix is actually doing. The question is, well, okay, I can see that it's doing something to my input vector. It's giving me some weird combination of them out again, but what is it doing? Is it making things bigger? Is it making them smaller in geometric terms? What is this matrix all about? That's what eigenvectors and eigenvalues are determined to tell you. They basically give you a better basis for looking at the matrix rather. Because you can see that the standard basis, and the standard basis is the one where, it's the one I used right here. It's where you assume you have 1, 0, and 0, 1, and the correct way to write a vector is 1, 0 times something plus 0, 1 times something else is equal to AB. Isn't really the basis that this matrix is working on. If I look at this linear transformation, it's not doing anything obvious to that basis. It's moving both of them around in funny ways. If I plug in 1, 0, I don't get something obvious out. What I get out is 1, 0 turns into 1 minus 1. So, okay, I plug in a unit vector in the x direction, and it ends up pointing diagonally downwards. And I plug in a unit vector pointing in the y direction, and that maps to something pointing diagonally sharply upwards. My brain, this hurts. This doesn't tell me really what the matrix is doing. That's what eigenvectors and eigenvalues are for. Basically what we're doing is we're saying, is there a basis where this matrix is obvious? Let's find out. And the idea here is, what we're looking for is are there any vectors which this matrix just scales? Doesn't twist, doesn't turn, doesn't skew, just makes bigger or makes smaller? Because those we could think about. My brain can handle making a vector bigger or smaller. And so what we want to do is we want to solve this equation. We want to say, well, okay, does it get bigger, does it get smaller? Well, we can subtract the right side from both sides. How can we do this? Well, we can cheat a little bit and say, well, this is the unit vector times lambda, so this is 1 minus lambda, 1, minus 1, 3 minus lambda, AB is equal to the 0 vector. This is just a linear algebra equivalent of subtracting the same thing from both sides. So we subtracted lambda 1, 0, 0, 1, AB from both sides. The matrix is subtracted over here. And we've got something far pleasant now. So now what we need to know is, are there A and B such that 1 minus lambda A plus B equals 0, and minus A plus 3 minus lambda B equals 0. Are there any vectors where this has a non-trivial solution? Sorry, what I mean by non-trivial solution is obviously I can plug in A equals B equals 0 and I get a solution. No problem. But are there A and B where this isn't obvious? Let's see. In particular, are there lambda where this isn't obvious? Well, if I try to solve this, what do I get? I get B is equal to minus 1 minus lambda A. And now notice, and I get, that would solve the first one. I get A is equal to 3 minus lambda B. And I say, well, okay, normally I can solve these. When can I not? And the answer is, the times this has a non-trivial solution is precisely when these things become linearly dependent. In other words, when this thing has zero determinant. That's one way to look at this. So what is the determinant of this thing? Well, remember a matrix. If this matrix is invertible, is another better way of looking at this. We're asking, when is this solvable? The answer is, this is solvable if this matrix is invertible. Because if this matrix is inverse, we multiply both sides by the inverse of the matrix, and bingo bango, A equals 0, B equals 0, and there's no interesting solution. So let's try finding the determinant. The determinant is 1 minus lambda times 3 minus lambda minus 1 times minus 1. And we want the determinant to be 0, equals 0. To find it out, we multiply this out by FOIL. Lambda squared minus 4 lambda plus 3 plus 1 equals 0. Or lambda squared minus 4 lambda plus 4 is equal to 0. Can we solve that? Sure, it's a quadratic. You plug it into the quadratic formula like any other quadratic. Lambda equals minus b plus or minus square root of b squared minus 4ac over 2a. And isn't that cute? We get, good heavens, dog. I apologize for the noise in the background. My dog has discovered a tin can and thinks this is the best thing ever. Over 2a, 2 is 1, so it's just 2. So lambda is 2, and there's a double eigenvalue there, which is kind of cool. So what happens if I plug 2 into this thing? Well, what I get is minus 1, minus 1, 1, 1. Sure enough, that's not an invertible matrix. So these things have interesting solutions if and only if lambda equals 2. So that's interesting. What this says is this thing scales something doubly. Let's see what it looks like. Minus 1, minus 1. When we have that vector times AB, we can actually just solve it right out. That tells us A equals B. So the interesting vector here is 1, 1. If we plug that in, 1 minus 1, 1, 3, 1, 1 equal 2. What does that do? It becomes 2, 2. There's when we can understand. If you plug 1, 1 into this vector, into this matrix, what comes out is a perfectly scaled vector. And that's really cool. This is the kind of thing eigenvectors, eigenvalues are for. What they tell you is what vectors do obvious things. In this case, well, one vector does something obvious. 1, 1. It gets scaled beautifully. Okay. Now this is an interesting one, of course, because it has a doubled value. How do we deal with that? Well, we're running out of time on the show. It's almost 9:30. We'll talk about that beginning of next time. This has been Nighttime FX Radio. So, time to sign off for this show, but in this weird world where the math classes have all stopped, but the homework goes on and on and on, we're here to help. Tune in Pacific time, 9 p.m. We'll help you with your math. Just tweet the Night Math Radio at Twitter. Good night, everybody.